So now that we have discussed the key air pollutants and the main sources, we're going to discuss now the transport of the pollutants. And the main transport of the pollutants is due to the meteorologic conditions. So to start discussing the transport of pollutants, we need to distinguish between variable gases and permanent gases. Variable gases are the gases whose concentration can change over time, and these are the ones who in recent history have been constantly varied. Also, there are some gases, as we have seen before, that the concentration even varies hourly or daily or between seasons or in years. And it is important to mention that these variable gases is only a small fraction, a very small fraction of the total amount of gases. And so these permanent gases that are the ones that are all the time in the atmosphere are, of course, the nitrogen and the oxygen, which together are the 99% of the gases of the Earth's lower atmosphere. So just to remember, in the troposphere is the 80% of the mass of the atmosphere. And the majority of the composition is water vapor that is related to the precipitation, clouds, and the movement of the meteorologic conditions. There is also a decrease in temperature, as you can see, that is depending on the height, right? And this is something very important for the movement of the pollutants. Then we have above this troposphere, we have the stratosphere, which is pretty stable and dry. And as you can see, the temperature variation completely differs from the troposphere. So in the stratosphere, we know that the UV is being absorbed by the ozone, and also in the stratosphere is where there is an increase in temperature profile, which is called also an inversion. So as we mentioned before, the troposphere is an unstable region, and it's unstable because it's dynamic, and is where the human impacts are being reflected. This complexity involves also dynamics that are at global, at regional, and at local scale. So the dynamic processes that occur in the atmosphere is what impacts the distribution of pollutants. And this is because the atmosphere can be seen as an engine that is continuously expanding and compressing gases. And this is because of the temperature and the pressure. And sun is the driving force. The sun gives a difference in temperature that allows the global circulation of the atmosphere. The ability of the atmosphere to disperse pollutants depends highly on this movement of wind and the direction of the wind, and this is related to the temperature profile. So from here, we can distinguish now two types of movements. One is the vertical movement of pollutants, that is the one that we're going to discuss at first, and then also the horizontal movement of pollutants, which is caused by the movement of air depending on the region in the planet. So if we look at the atmosphere as a region where air expands and also compresses, we need to talk about the adiabatic process that occurs. So we know that according to the first law of thermodynamics, we have that the energy of a system depends on the heat that is being transferred and also the work that is being done. When we're talking about an adiabatic system, we're talking that there is no exchange of heat. So no heat is transferred across its boundary, and we're going to imagine that the boundary of the system is very, very large. If we remove the heat component, then we will end up with internal energy and also with the work. The internal energy can be translated to the specific heat of air at constant pressure, and also times the delta or the delta of temperature, of the incremental temperature change. Then on the other side, the work it can be transferred to the volume per unit of mass times the incremental pressure change in the air parcel. So let's look at the more in detail about what are we talking about here. So we're talking about a column of air in static equilibrium, and we're talking that the pressure changes with the altitude, right? With the altitude. And this change in pressure is dependent on the gravity and also on the distance. So we can translate the change of the pressure over the distance, which is equals to the gravity times the density of the air. So after doing some arrangements on these two equations that we have mentioned before, which is the change of temperature over as a function of the pressure and the change of pressure as a function of the distance, we can come up with an equation that will tell us the change of temperature over the distance, which is dependent on the gravity and on the specific heat of air, because we can cancel in this case the density and also the volume, because these ones will have the same units. So now we know that the change of temperature over the distance is equal to the negative value of the gravity divided by the heat capacity, and this gives us a value of approximately minus 10 Celsius per kilometer when we do the conversion, the proper conversions of units. So this means that an air parcel, if it's moved 1 kilometer of distance away from the ground, it should decrease 10 degrees Celsius ideally. So this value, or this line, will give us the definition of atmospheric stability, because this line will be the reference to know whether the system or the air is on unstable conditions or is on unstable conditions. This is the relationship between the ambient lapse rate and the dry adiabatic lapse rate, and it determines the stability of the air and also determines how the pollutants disperse. We also have the moist adiabatic lapse rate, and if you notice, the change in temperature is slightly lower, and this is because the water requires a higher amount of energy to have a change in temperature. So the actual adiabatic lapse rate will depend on factors like wind speed, sunlight, and geographical features. So to understand what is atmospheric stability is how difficult is that the conditions will change. If we're talking about an unstable equilibrium, it means that it can constantly vary the conditions. And if it's a stable equilibrium, it's going to be very difficult that any disturbance will affect the system. In a stable atmosphere, a rising air parcel is cooler and more dense than air surrounding it, and if given the chance, it will return to its original position. You can imagine now what conditions do we want for the dispersion of pollutants. We don't want really stable conditions, because that will mean that there is no movement of air, which means that the pollutants will remain in the parcel of air for longer period. So when there is a significant decrease of temperature over the distance, which means that the decreasing temperature is higher than 10 Celsius per kilometer, we're talking about a superadiabatic ambient lapse rate. So it's a very unstable condition. On the other hand, when we're talking about a slight change of temperature or a smaller change of temperature over longer distance, we're talking about subadiabatic ambient lapse rate. And this means that we have stable conditions. But this really lapse rate is always changing. It changes during the day because of the solar radiation. It also changes because of topographic features, and also it is influenced by other components in the troposphere. So now that we understood what is the adiabatic lapse rate and the moist adiabatic lapse rate, can we now define the conditions of the system? So we're going to consider now a situation where the environmental lapse rate is measured at 0.8 degrees Celsius per every 100 meters. And the dry adiabatic lapse rate is 10 Celsius per kilometer. If there is no wind in this situation and the air parcel is not saturated, which means that there is no humidity, then the atmosphere can be considered inverted, layered, stable, neutral, or unstable. Well, in this case, the answer is stable. When we convert the units of meters to kilometers of the 0.8 Celsius divided by 100 meters, we can see that this value is less than the dry adiabatic lapse rate, that is 10 Celsius per kilometer. So therefore, a parcel of air that is elevated will cool as it follows the dry adiabatic lapse rate. As a result, it will be denser than the surrounding air, which will prevent it from accelerating upwards.